This week in statistics, we're going to be playing with linear models, also called linear correlation. We're playing with two quantitative variables. So one important thing here is getting used to lines again. And we can play around with data with respect to lines, either in Google Sheets, StatKey, Excel, or TI-84. Textbook is very important here. It's going to review the ideas of lines and then slope, and how we use the idea of linear regression, which is a way of modeling. I have a couple of special websites you might want to check out here. One, and this is just an amazing graphical display of data. Got a ton of other stuff on this website. I highly recommend you check it out. So here we have income per capita versus life expectancy. And each of these dots here is a country. And you can see, as you point to one, it tells you what the country is. But as income increases, life expectancy increases. The size of each of these bubbles is the population. And you can play around with what the size of each bubble means. You can also play around with the horizontal and the vertical axis here. So this is an amazing site to play around with the idea of correlation, which is the relationship between two variables. Spurious Correlation is a website that throws together variables that really have nothing to do with each other, but you can see some trends, which is both great and not so great. And I'll come back to that later. You have a few assignments this week. You have your practice problems, which is just getting used to plotting points, making lines through those points, and interpreting the results. Critical thinking, you have a few questions to answer about the technical aspects of the lines we're putting to these data. And then your application this week is to find a pair of data sets that you can model using a line, and then to interpret some things about that data and line. And my recommendation is you go to StatKey to do that. So some examples to play with here. So again, we're doing linear models with two quantitative variables. So here, time is just kind of going by. Usually time is not a variable we play with directly. It's kind of an indirect variable, but sometimes we'll use it directly. Here I'm using it directly. So I have years after 1990 to kind of simplify the x-axis here, and I have the minimum wage in the United States. And you can see that over time, the minimum wage has been increasing. And I picked this data set because it's pretty easy to work with. And I had my spreadsheet program, Google Sheets, draw a line that Sheets thinks is the best line for this data. So how do we figure out the line of best fit? Well, you can often kind of just draw a line that you think will work well. And so I can just kind of play around estimating a line, like maybe I would try to go from the first point to the last point. And I can see here, I almost hit 3 of the points, but there's 2 below. So it seems like this is not the best fit because although I hit 3, 2 are underneath, I'm not kind of splitting the difference there. So maybe I should try and change the slope a little bit. So now I hit 2 of the points, and I have 2 above and 1 below. And you can just kind of play around trying to find a line that might be the best fit. All right, so here I hit 1, and I have 1, 2, 3 above and 1 below. So what is the best line for this data? And you can kind of play around trying to find something that fits fairly well. So here, I'm kind of hitting 1 at the base. And then I have almost hitting 1, 1's above, 1 below, and 1 way above there. A couple of questions might come to mind is, what's the equation for the line I just found right there? And we can try and estimate that. So I'm just going to mess with this one more time. I'm going to say it's going to go through that point right there. And I'm going to shift it up a tiny bit and say it goes through the middle point right there. All right, so reminder about lines. So the 2 points I believe this line is going through are the point 0, 3.25, because I'm trying to hit that first point right there. And I'm trying to hit that middle point, which is the point 10, 5. So that's this third point right there. I'm trying to go through the two of those. So I want to find the slope. So slope is rise over run. So the rise to get from here to here is, let's see, I'm trying to get from 3.25 to 5, so that would be about 1.75. And the run would be 10 years. So my slope, in this case, oops, would be going up 1.75 and dividing by 10, which is approximately 0.175. So I think that's the slope of this line. Now, because I chose this to be years after 1990, this point right here is my y-intercept. So you might remember the equation y equals mx plus b. M is my slope, and then the y-intercept is where it hits the axis. So I think this line right here could be modeled by 0.175 times x plus 3.25. So that's just a visual guess at a nice line that goes through these points that models them. And so the point of this is then I can use this line to say, hey, that's 15 right there, that's 20, so somewhere in between here is 18. That's years after 1990, so that would represent 2008. And so I can use my line to try and estimate what minimum wage might have been or should have been in 2008. So I can see here it's just under 7. And I could use a computer to help me figure that out by just plugging the x value 18 years after 1990 into my equation right there. So let's just try that. So I had a slope of 0.175. I looked at that 18 years later, starting off with 325. And so this says it's going to be like 650, 647. Let's see, how does that look on my picture? Yeah, 6.5, 7 would be over here. Yeah, that's okay. So that's reasonable on my picture. So here's my model, my linear model for this right here. Now, we could guess all day at the line, but everybody could guess slightly different. And how do we determine which is the best line? So picking a best line, it turns out there is a mathematical technique for that. So the way that works is this line actually doesn't hit any of these points, it turns out. It's just close. For every point, there's the line predicts a y value, and then there's the actual value. And so we can look at this vertical distance between them. And here we have a slight underestimate of the line. Here we have another underestimate. Here it's pretty darn close. Here the line is an overestimate for the actual data point, and here the line is an underestimate. And mathematically, we try to find the best line is by reducing the error. So what we're trying to do is find the minimum error in approximation in our line. And finding the minimum error gives us a technique called least squares. Least squares is also referred to as linear regression. And the linear regression line minimizes that error in approximation from the line to a point. Okay? And what we're minimizing there, the error is the error in the y, and y is our prediction, because we have something that looks like y equals mx plus b. So that's designed so that we plug in some x value, and then our output is the y value. And our output is our prediction. So we have two variables. We can plot those two variables and get a scatter plot. A scatter plot is just a collection of points. And then if the points kind of line up, then we can try to find a line to it. So here's a few other examples of that. So here, I like to mountain bike. So generally speaking, the longer I bike, the farther I go. And so here I have some times of mountain bike rides I've done recently versus the distance. And you can see that there's kind of a general uphill trend to the points. And I asked the computer here to find me a linear model to go with it. So the computer is saying that the model here, y, my distance, versus x, my time, is 7.09 times the time I rode plus a little bonus of 1.35. And so this is going to give me distance based on time. And it gives me another piece of information here called r squared. R squared is the coefficient of determination. Just run a lot of room there. And what the coefficient of determination is, it's a percentage. So I'm going to call that 0.7, would be 70%. So what that means is, given a particular time, distance, the time with 70% accuracy predicts how far I biked. And again, you can see that they don't line up perfectly. There's a little variation. So the variation in time versus the variation in distance. So I have kind of a 70% accuracy rate in predicting distance versus time. So that's kind of what the coefficient of determination tells us. All right, so let's take a look at another example. We got all week to play with this. So here I found some data on flu cases versus flu deaths in a particular region. And you can see, so blue is cases. So as cases goes up, deaths goes up based on the flu. As cases go down, deaths based on the flu goes down also. And that kind of makes sense that we'd have that kind of relationship. More flu cases, more probable deaths based on the flu. If you plot that in a slightly different way, instead of a time series graph like I have here, if you just plot the particular number of cases related to the number of deaths in that particular year, you can see they line up pretty damn good. Okay, so the time series graphs are giving us a hint that these two correlate, meaning that they either increase together or they decrease together. And so when I make that as a scatter plot, I can put a line to it, and then I can use this to say, okay, if you know, we're predicting 75,000 cases of the flu, then we're probably going to end up with 48,000 deaths that year. So again, it gives us a relationship between one variable and the other. Now, not all relationships are linear, some curve. We're just focusing on linear relationships here. Okay, so two variables could correlate, but they may not be linear. Here, we're just focused on linear stuff. So we're going to start off with the most basic kind of relationship between two quantitative variables. All right, tools we have to play with this. So one tool is StatKey. And StatKey comes with a whole bunch of data that you can play with. So if I just search for StatKey, I want to play with their interface, and I'm looking at two quantitative variables, descriptive statistics at the moment. They have a whole bunch of different data sets. So let's take a look at cricket chirps. So here, the number of chirps a cricket makes versus the temperature and the environment the cricket is in. And you can see that the higher the temperature, the more chirps a cricket makes. So there's a correlation here between temperature and chirps. Now, just because there's correlation, meaning as one goes up, the other goes up, or as one goes down, the other goes down, it doesn't necessarily mean that there's causation. So do the cricket chirps make the temperature increase in the environment? I don't think a cricket can change the environmental temperature. It could go the other way. Maybe the temperature affects how much the cricket chirps. Okay? So causation is one variable. There's some kind of reason that it might force another variable to change. And you just never know about that. So for example, if I take a look at the spurious correlations, There's instructions on how to play with that here, but I'm just going to go straight to his main website. Spurious means questionable. So here he has US spending on science, space, and technology versus suicides by hanging, strangulation, and suffocation. So the more hangings and suffocation, strangulation deaths there are, the more likely we are to spend money on science. That doesn't seem reasonable, right? That's nuts. But it turns out the two do increase together. Okay, so there is correlation here, but causation is questionable. Another one, number of people who drown by falling into a pool versus films by Nicolas Cage, right? So films by Nicolas Cage, how many films he made in a particular year versus drownings. And these two do seem to change together, which is kind of crazy. So there's correlation, but causation, do the number of drownings influence how many movies Nicolas Cage does, or does Nicolas Cage making movies somehow affect people drowning? I don't think so, right? Crazy stuff. Per capita cheese consumption versus people who die by becoming tangled in their bed sheets. There's correlation, excuse me, in that they tend to increase together, but I seriously doubt cheese consumption and strangulation by getting tangled in your bed sheets, that they tend to be related. So causation is unlikely. So correlation is one thing. That's a mathematical measurement of whether two things seem to change together. Causation is some reason that those changes happen to happen. And those are two totally different things. Correlation does not imply causation. All right. Let's see, a couple of other examples I got here. Back to the minimum wage thing. So it turns out when you find the line of best fit, it's always going to go through the average X and the average Y value. So here I'm taking a look at finding the mean point of a data set. So the average X value is 10, right? That's right in the middle. Turns out the average Y value is 4.95, which is pretty darn close to 5. And if we look at my graph on that, minimum wage, let's move this one out of the way. You can see that that line pretty darn closely goes through that middle number right there, okay? So the mean X, mean Y, that particular point is on the line of best fit. So here I've plotted those points, and now I'm going to estimate the line of best fit by using the line tool here. I'm going to click on that middle point because it's pretty close to the mean XY value. And then I'm going to try and split the difference as best I can here. So maybe about right there. So that looks like a pretty good line here. Notice how it models that very well. All right, so other tools we have to work with are a spreadsheet. So let's take a look at a spreadsheet. Let's look at the mountain biking one again. So I'm just going to recreate this for you. So given a set of data, put it in a new tab. And my preference is a spreadsheet, but StatKey works pretty awesome. I'll show that too. If I want to make a graph out of these two, I highlight the data, and I like to highlight the titles. And then I use the Insert Chart option. And I don't want a column chart, I want a scatter plot. Once I have the scatter plot, I look at it and say, do those kind of sort of line up? And I'm going to say, yeah, they kind of sort of line up. So just some editing things. The data I selected here, let's move that a little, has a first row that has headers. So I'm going to select use row 2 as headers, and column A are my labels here for the horizontal variable. And I'm going to customize it. And it's going to be a good idea to eventually put in better titles, because right now it doesn't have very good titles. It's none. But what I want to do is check out the series. And Excel is pretty similar for you Excel users. I'm using Google Sheets. What I want to do is I want to insert a trend line. I want to label that trend line with the equation, and I want to show R squared, that coefficient of determination. If you take the square root of R, squared, you get R, and that's the correlation coefficient, and that tells us something else. Check out the book for what the correlation coefficient tells us, but here I'm going to focus on the coefficient of determination. So then it throws that in there, and it also gives me the equation of it. So here it's telling me that the equation it's telling me part of it, so I would say y equals 7.09 times x plus 1.35. So it's telling me the y-intercept, and it's telling me the y slope. And then it also says that r squared is 0.7, which is the percent that the independent variable predicts the variation in the dependent variable. So my independent variable is the time, my dependent variable is the distance. All right, so what does that mean? Let's write that down, do a quick interpretation, and then we're done for now. Come on. All right, here we go. So, new page. So I've got y is equal to 7.09x plus 1.35. Y, remember, is going to be the distance in miles that I biked, and x is the time in hours. Slope, remember, this guy right here, slope is rise over run. So I'm going to say my rise is 7.09 and my run is 1. My rise, that's the vertical variable, right? My vertical variable is y, that's distance, that's miles. And my run, that's my x value, my horizontal variable, that's hours. So in order to figure out what this equation means, you pretty much got to think through what each variable is. So this tells me that for each additional hour, because this is slope is a change, right? Slope is a rate, which means fraction of change. Each variable is changing. So for each additional hour, that's my independent variable, I can bike, it's supposed to be a K, 7 more miles. Okay, so that's my slope here. So the mountain biking I do lately involves a lot of hill climbing, so I'm a little bit slow. It's a lot of uphill stuff. All right, so that's slope. Y-intercept, on the other hand, that's this number right here. That's a point on the graph. It's the point 0, 1.35. So what does that mean? 0 is hours, and 1.35 is miles. So that says if I go no time, I've already biked 1.35 miles. But, all right. So in this case, the y-intercept doesn't make physical sense. So what I should find is that if I went 0 hours, there should be 0 miles. So this line theoretically actually should go through the point 0, 0, but it doesn't for some strange reason. Who knows why? Every situation is a little bit different. If we look at the example of, oh, wrong button. Try that again. There we go. If we look at the example of the what's that first one I had? Minimum wage. Okay, so I had there the y-intercept was about 3.25, let's call it. And the slope there, let's see, do I have that visible here? Okay, so one of my lines I came up with was 0.175, 3.25. All right, let's use that sucker. Sheets. All right, so I have another example here where I have y. Let's come on, pen. Y equals 0.175 x plus 3.25. Let's interpret that. So the y value in this case was the minimum wage, and that would be in US dollars, and x is the year after 1990. Slope in this case, remember slope is rise over run. In this case, the rise is the change in dollars, and run would be the change in years. And I have 0.175 over 1, and that's going to be dollars per year. Right? So what I can say is that each year, each additional year, so right, because the slope is a change, it's a rate of change, each additional year, the minimum wage increases by about, let's round that, 18 cents. Okay. So that's an interpretation of the slope. The y-intercept, on the other hand, right there, so x is years after 1990, the y-intercept is always the 0.0, whatever the y-intercept is, 3.25. So this would be 0 years after 1990. So the y-intercept means that in 1990, the minimum wage was $3.25. So in this case, the minimum wage is, the y-intercept, excuse me, is meaningful, right? It means something. And every example is different. Other things to consider besides interpreting the slope and the y-intercept of a linear model that we find for the data is, can we use the model to predict stuff? So what if I biked for an hour and a half? Would I be able to predict about how far I can go? And so here, on this particular model, let's scroll a touch. If I went for 1.5 hours, and then I trace over, it looks like I'm going to go about 12 miles according to this model right here, right? Somewhere in between 10 and 15, a little below the middle. So I can, within the data set, when I use the line, the equation to make a prediction, that's called interpolation. Let's write that down, another important idea. So that is to make a prediction with your model within the data set. Now, suppose this is my data set right there, and let's say this is my line right there. If I then try to use the model to go outside of my data set, so like way out here, let's suppose this is my biking, this is some time to bike, and then this correspondingly would represent some distance when I trace to figure out what point I was at. When I go outside of the data set, with the model, that's called extrapolation. And extrapolation can be dangerous. So this predicts that I can bike as long as I want and I can always find the distance. Well, it turns out I can't bike forever. There's going to be a certain amount of time for which my body just kind of gives out and I can't bike anymore, right? So this model is only good within a certain time frame and a certain distance. Okay, how many miles can I bike in a day? I can't bike forever. This line goes on forever, but time and my body cannot. Okay, so extrapolation can be dangerous. But ultimately, we do want to be able to extrapolate a little bit with these models. We want to predict just a little bit outside of the range that we have, but we got to be careful as to how far we try to go outside of the data set. And that's called extrapolation. So interpolation, going within the data set, that's usually relatively safe. Extrapolation, trying to go outside of the data set, that can be a little more dangerous, and we have to be careful there. We do hope that models can help us predict a little bit in the future. However, there's only so far we can go before things start to get too sketchy. All right, I hope this was useful and you enjoyed this math as much as I do. This is one of my favorite topics. It's awesome, it's powerful, it's cool. Have fun, do good math. I'll see you in the future.